Okay, second installment on working on this practice exam. Last time we did the first 6. There are 18 more problems in this practice exam, 24 altogether. So we're going to do another 6 right now. The first 6, of course, were the final exam from 2 years ago. These next 6 are just random representative problems of various sorts. So the very first one is of the remaining ones is something to do with StatMech, is a statistical mechanics problem. Let's just read it first and then we'll go through it. A quantum mechanical harmonic oscillator has an infinite set of quantum states with equally spaced energies. Here are the energies, but they keep going to infinity. All the energies are equal to some quantum number n times a gap size. So the little Greek epsilon there is a gap size. And depending on what n is, you either are on 0, you're on 1, you're on 2, you're on 3, and you're on 4, and so on. Write down the mathematical expression for the canonical partition function Q for this system in terms of the quantum number, the gap size, and the temperature. You don't need to actually evaluate the sum, and the reason is because the actual sum is given down here anyway. But the problem wants you to write down the math of it. Remember that the partition function, the definition of the partition function is, let me give myself a little bit more space here, is that it's the sum over all microstates of the system, e to the minus energy of that microstate over, well, either RT or KT. Let's see, I used KT here, so we'll use that, depending on whether the energies are in macroscopic or microscopic units. So in this case, there's an infinite set of microstates here, and the quantum number n starts from 0. N goes from 0 up to however high you want to go, up to infinity. And so our summing over, and there's one microstate for each n value, so our sum is going to be n equals 0 up to infinity of e to the minus e for n divided by kBt. E for n is equal to n times epsilon, and so this just becomes n equals 0 to infinity e to the minus n epsilon over kBt, and that's Q, and that is the answer for the first one. This one sounds a little difficult to begin with, but if you just apply the definitions and what you know, it turns out not to be that hard. Now, actually turning this infinite sum into something useful, something that isn't an infinite sum, is a little bit harder, and that's a bonus problem at the end of this. I almost never give bonus problems in actual exams, but this was just a practice problem, so I put a bonus part in there. We'll look at that a little bit at the end of the problem. It's not the most important part of this problem by any means, but we'll look at it anyway. All right, the next part of the problem says, here's the partition function. Turns out that infinite sum can be reduced to something pretty simple, and it gives the value for the gap size, 5 kilojoules per mole, and T is 300 K. Then find the population, the actual probabilities for the first 3 states corresponding to n equals 0, n equals 1, or n equals 2. Well, that just uses the standard relationship that the probability for state I is equal to e to the minus energy for state I divided by kBt divided by Q, and now we have Q. So if I plug in the expression for Q that's given in the problem here, there it is. That's 1 over 1 minus e to the minus epsilon over kBt. And that's equal to 1 minus e to the minus epsilon over kBt times e to the minus, now I'm going to plug in here, n e epsilon over kbt, where n in our case is going to be either 0 or 1 or 2, right, for the three probabilities that we're after. So probability P0 would be 1 minus e to the minus, well, let's calculate q first, because we're going to need that over and over. We're going to need that all 3 times, so let's calculate q first. Q is equal to 1 minus e to the minus 5 kilojoules per mole divided by, and it's given in kilojoules per mole, so I'm going to change this to an RT. And since it's at 300K, it's 2494, right? And that is equal to 1.156. And then P0 is equal to e to the minus, n is equal to 0 here, so it's e to the minus 0. It's just a 1 over 1.156, and that is equal to 0.856. The next one, P1, is e to the minus, now this n is a 1, so it's 5,000, that's epsilon, over 2494 again, over 1.156, and that is equal to 0.117. And finally, P2 is equal to e to the minus 2 times 5,000, right? 2 epsilon over 2494 divided by 1.156. And that is equal to 0.016. It's always good to check at the end that these things add up to 1, because they, well, actually, sorry, in this case they don't, right? Because there's a bunch of other states. But notice that the probabilities are getting awfully small even by the time we've gotten to n equals 2. So if we go to n equals 3, it's going to be much smaller yet. So probably these ought to add up to close to 1. They won't add up to exactly 1. Let's just do it. 0.856, 0.117, 0.016, 6 and 7 and 6 is 19, 6, 7, 8, 8 and 1 is 0.989. Okay, so there's a little bit of probability in all the rest of the states, but yes, these probabilities are heading quickly towards 1. All right, that's the first 2 parts. Let's talk about that bonus part down at the bottom now. It's just a pure mathematical problem, really. What is this sum equal to? So n equals 0 to infinity e to the minus n epsilon over kbt. Well, the trick, there's several tricks here. The first one is to notice that all of this stuff is just a constant, and so we can call the quantity x equal to e to the minus epsilon over kbt. And if we do that and substitute in here, then this becomes just n equals 0 to infinity x to the nth power. So we're just summing powers of x. Even though x is this complicated thing, in the end, from a mathematical point of view, it's just summing over the powers of n. I will tell you that many people, including myself, will recognize that infinite sum right away. It's equal to 1 over 1 minus x. But the little key here shows a way to prove that. There are several different ways of proving it, in fact, but this is a nice one. We do it in the following way. We say that q is equal to the sum from n equals 0 to infinity of x to the n. But since we're starting from 0, that the first term in this infinite sum is a 1, right? It's x to the 0 power. So it's 1 plus x times the sum from n equals 0 to infinity of x to the n. In other words, if I just multiply this x in on every one of these, it gives me all the remaining terms after I've left out the first one. But it turns out that since this is an infinite sum, that's the same thing. This is q again, right? So we get that q is equal to 1 plus x times q. And now we just have to solve for q. Q times 1 minus x is equal to 1, and q is equal to 1 over 1 minus x, which is equal to 1 over 1 minus e to the minus epsilon over kbt. which is in fact the right answer, right? That's the answer that's here and also was here, yeah. Okay, that's number one. Number two in this particular case is another thermodynamic, calculate quantities Q, W, delta H, delta S, and so on around a loop. We did one of those up at the top. This one's not terribly different. There is one thing that should be pointed out, though, and that is, notice this diagram isn't a PV diagram, it's a TV diagram. And that means that, for example, a constant P step is a slanted line instead of a straight up and down line. And it also means that this step isn't a constant P step, it's a constant T step. But all those things are not difficult as long as you don't miss the fact that this is temperature over here. Most of the time on these diagrams that's pressure, right? But in this case it's temperature. And let me say, the diagram like this is also a very common case. In our class, I've tended to use PV diagrams, but that's not at all the only thing that ever gets used. And so, yeah, temperature and pressure, temperature and volume, pressure and volume, all the possible combinations, pressure and mole numbers, and so on, all the possible combinations get used. So because this is basically a standard problem that we've done many times already and also very long, I think I'll just skip over this. I think the key itself is relatively self-explanatory, and I don't want to waste the time going through it. So if people have questions about it, email me or something. The next problem, let's read that one like we did before. It says protein P is a short peptide with 20 amino acids. That's something, let me just write down what we are going to need here. First of all, let me clear off some of this garbage over here. So we have some empty space again. And let me shrink this a little bit. So we've got 20 AAs. And it's going to start as a random coil, unfolded, but it can fold into an ordered structure, and we call the random coil R and the folded structure F. So this is a short peptide that can fold or unfold. Upon folding, most of the entropy is due to internal rotation of the internal rotational freedom of the residues, delta S chain, is lost. The residues get locked up. But water entropy may be increased due to the hydrophobic effect. So there's another contribution to delta S, which we'll call HPE here, due to the fact that once it's unfolded, the residues come in contact with hydrophobic residues, which the water comes in contact with hydrophobic residues, which reduces the water entropy, right? That's the hydrophobic effect. And also release of bound water. So when it folds, it sequesters the hydrophobic residues away from water and also possibly releases some water. So we'll call that R water. R release, actually. Water release is what I called it down below, so let's stick with that. So those are the three contributions to delta S. The residues may interact more favorably with each other by H bonding and so on when they're folded, leading to an enthalpy change, delta H, residue, RR, but favorable interactions between residues and water may be lost. So there's a delta H of interaction between residues and the water, and that gets lost when, well, some of it at least gets lost when things get folded. And all right, that's the description of the system. It says then let the overall entropy change be just the sum of these three guys, as you'd expect. Those are the three contributions to delta S. Delta S fold, it's called. And also that these two guys are delta H fold. So the folding, we're looking here at the unfold goes to fold reaction or transition. All right, first question then. If each residue has 10 rotational states when it's folded, but is locked into a single state when, 10 rotational states when unfolded, but locked into a single state when folded, find the appropriate change in chain entropy, delta S chain. So we're obviously going to be using delta S chain is equal to, let's use macroscopic units, so R log W when it's folded over W when it's unfolded. That's what it asks for, yes. What's the approximate change in chain entropy? Well, it doesn't say which way, but that's the way it's got to be. And yeah, that's what I have here too, W for F over W for R. Okay. So we need to know what W for F and W for unfolded are. Let's call them big F and R. That's a better, simpler thing to do. So this is F and this is R. W for F is just equal to 1, right? All the residues, all 20 of the residues get locked into one configuration. That's obviously an approximation. That's not really true. But that's what we're saying for simplicity's sake. And WR is going to be what? Well, it says that there's 10 rotational states when unfolded per residue, but a single state when folded. And so there will be 10 rotational states, but there are 20 residues, so 10 to the 20th power. And therefore, delta S chain is equal to R log of that guy over that guy, which is 10 to the minus 20th power. And all that remains is to do the arithmetic, and it gives you minus 382.9 joules per K per mole for the answer. The important thing here, of course, is not the answer. It's the logic of setting up the calculation in the first place. I'm trying to keep my key clean here a little bit, so getting rid of all this junk while I can. I think there's some junk up here. Yes, let me clear that up too. All right, and I think that's it. Everything else has already been cleared out. Okay. So that's the first part of the problem. The next part says if all residues are hydrophobic and each residue excludes 2 waters, so that there's 20 hydrophobic residues, because they're all hydrophobic, and each one releases 2 waters when, in other words, 2 waters that were in contact with those hydrophobic bases before things fold, but when they fold, then those waters are pushed out of the system. They're not included in the folded form. And let's suppose it says that each excluded water gains 2 rotational states. That means that for every amino acid, the 2 waters getting excluded will gain a total of 4 states, quantum states altogether. And there are 20 of those. And, well, I wrote times 20, but that's wrong. It's 4 to the 20th power, because there's 4 for each of them, and they're all independent. So then, what's the delta S contribution in this case? Delta S HPE is going to be equal to R log W folding over W unfolded. This is the gain, so WF is 4 to the 20 over just 1 for WR. And so HPE, delta S HPE is equal to R log 4 to the 20th power. And the rest is arithmetic. Let's just make sure I haven't made a mistake. No, that looks right. I did it a little differently here. Notice I said instead of 4 to the 20th power, I said 2 to the 40th power, But that's the same thing, right? 4 is equal to 2 to the 2, so 4 to the 20th is equal to 2 to the 2 times 20, which is 2 to the 40th. And I also played this trick. I did this above too, but I didn't point it out, that when you take something like this, right, r log 4 to the 20th, or r log 2 to the 40th is what I used there, then that's the same thing as r times 40 log 2. That makes the calculation easier, right? You don't have to take anything to the 40th power. So that gives you 230.5 kilojoules per mole. Again, it's the logic of setting these calculations up that's the important thing. Finally, it says that let's suppose that when the whole protein folds up, it releases 5 waters that were bound. So these are waters that are released when the folding occurs. In other words, another gain in entropy due to folding. And let's suppose that each water gains about 5 kilojoules per mole of translational entropy every time it releases. So in this case, it doesn't give us a number of states. It gives us the contribution from each water. There's 5 of them. 5 times 5 is 25. So that one was easy. All right, that's the entropy. The next contribution is from the enthalpy, enthalpic contributions. It says the net favorable interaction enthalpy between residues is about minus 12 kilojoules per mole. So when the A's come together, it's minus 12 each one. Net, depending on all the interactions. They're just 12 kilojoules per mole stickier when they're together than when they're apart. But you lose some interaction with water, and that's 10 kilojoules per mole, so the net is only 2 kilojoules per mole per residue. There are 20 of them, so it's minus 2, so it's minus 40 kilojoules per mole, and that's the answer for the delta H of folding. Pretty straightforward and simple for that one. And then the last question says, let the denaturation temperature, that is the melting temperature if this were DNA, but basically the unfolding temperature, be defined as the temperature at which the concentrations of folded protein and unfolded protein are the same. Assuming that neither delta S fold nor delta H fold changes with temperature, derive an expression for the denaturation temperature in terms of delta S fold and delta H fold. So what we want is that, in effect, the delta G favoring for folding or unfolding is equal, which means delta G has to be equal to 0. That's delta H of folding minus T delta S of, what did I call it? Delta S of fold, yeah. And that's the TD that we want, that temperature is. Therefore, TD is equal to delta H fold over delta S fold. And that's actually the answer, because it doesn't actually ask for a number. It really only asks for the expression, and that's it. TD is equal to delta H over delta S. However, since we have the numbers from above, I plug the numbers in. It's 40,000, right? 40 kilojoules per mole minus 40 kilojoules per mole for delta H. And I summed up all 3 contributions from delta S in the denominator here, and that gives a melting temperature of 314 K, which is reasonable. Of course, I adjusted all the numbers, so it would be reasonable, so that's not surprising. 314 K is, well above body temperature or room temperature, but not at boiling temperature or anything like that. And this is a small peptide, so that's actually maybe even a little bit high for the melting temperature of such a small peptide. All right, that's problem number 3. Problem number 4 is a predict the delta H and delta S and melting temperature problem for an oligonucleotide that has 1, 2, 3, 4, 5, 6, 7, 8, 9 base pairs. And all the base pairs are almost the same, right? There's a GC tumor there, and then there's a CG one, but they're all the same after that. And let's just count them. There's a GC there, there's a GC there, a GC there, a GC there. So that's 4 GCs. And then looking at the other ones, the CGs, there's 1, there's 2, there's 3, and there's 4. So there's 4 CGs and 4 GCs. And that's going to make the calculation easier. There's also these 2 N groups, and they're both GC N groups, so everything should be pretty straightforward. So therefore, the delta H of annealing should be 2 times the GC, the terminal value for GC, 4 times the delta H for GC, and 4 times the delta H for CG. The table is down here at the end. I won't go down there. But the values taken from that table are 0.4 for the terminal groups, minus 41 for the GC case, minus 44 for the CG case. Notice that GC is not the same thing as CG, so yeah, don't confuse those two. And adding things up gives minus 340.8. Doing exactly the same thing for delta S gives minus 887. And now we have this formula for predicting the melting temperature, delta H melt over delta S melt, minus R log CT over 4. And the only trick at all here is to remember that these values that we just calculated, this one and this one, are for annealing. They're not for melting. It's the negatives of those that we need for melting. So just putting a plus sign, and these are both negative, right? So putting a plus sign in front of both of them, it's 340 on top, 887 on the bottom. And the concentration is 1 millimolar. That's what goes in there. And if you do the arithmetic, that turns out to be 356.5 K, which is what? Just below the boiling point. So this is a, what is that? That's, let's see, that's 27 plus 56 is 70, 83 degrees, which is very reasonable. Actually, it's a little high. The melting point for a 9-mer like this is probably a little lower than that. Typical melting points for long DNAs are in the 80s. But anyway, that's the answer we get. All right, that's number 4. Number 5 looks complicated because it's a long bit of verbiage there, but it's actually fairly straightforward and simple. I don't think we'll need that this time. So let's read it again. The standard mechanism for replication of DNA by DNA polymerase is this mechanism, which we looked at extensively in the lectures, of course, and here's that mechanism written out in steps. Notice K1, K minus 1, K2, K3, K4, K5. So a total of 6 different steps, 6 different rate constants. The first thing it asks is, what are the intermediates in this mechanism? Well, the overall reaction is this CN stands for the complex of polymerase and DNA with N nucleotides. And so CN plus NTP, well, it's given up here actually. CN plus NTP goes to CN plus 1 more base pair, plus the pyrophosphate that's released. That's the overall reaction. Everything that's not in the overall reaction is an intermediate. And so, let's see, C.NTP is an intermediate. There's that A is an intermediate, B is an intermediate, CN plus 1.PPI is an intermediate, and I think that's it. So those 4 are intermediates, and here they are listed. That's pretty straightforward. And then it asks you to write the actual rate equations for 3 of the species, CN, 3 of the intermediates actually, CN.NTP and CN plus 1.PPI. Let's just do one of them in the interest of time. I think most people, in the last exam, most people got this absolutely correct, so don't think we need a whole lot of practice on this stuff. So let's just do one of them. Looking at the mechanism, I'm going to do this one, Cn.ntp. So this one appears here, it appears there, and it appears there, so it's going to, and nowhere else. So there's going to be three contributions to its rate equation. The Cn dNTP dt is going to be contribution from reaction 1, and it's a product, so a plus sign. Rate constant is K1, and then it's second order, right, in Cn and NTP, so it's K1 times Cn times NTP. Contribution from number 2 will be, and it's a reactant this time, so a minus sign. Rate constant is K minus 1. And it's first order going this way, right? Cn NTP just falling apart, and so it's just proportional to the concentration of Cn NTP. Third contribution is from reaction 3 here. It's got rate constant K2. It's first order, it's a reactant, and so it's just going to be K2 minus K2 times CNTP. And we could do the others too, but I think those are pretty clear. Clean this up. That was number 4. That was quick. No, that was number 5. That was quick. And finally, the last one that we'll do for this lecture is a standard, pretty much standard Arrhenius problem, except applied to DNA polymerases, of course, like everything. DNA polymerase achieves high fidelity by testing each incoming nucleotide against its shape. This is all familiar, I hope. This test occurs when the finger's domain tries to close, forming a tight pocket needed for catalysis to occur. This is the rate limiting step. So anything that affects its rate constant, K2, directly affects the overall turnover rate for the enzyme. So K2 is 200 seconds to the minus 1 at 300 K and 250 at 310 K. So notice 250, let me get some space here. K2 is equal to 200 at 300. K2 is equal to 250 at 350. Remember the rule of thumb. Sorry, not 350, 310. If you go up by 10 degrees like we did here, then the rate would double if you have a barrier of 50 kilojoules per mole. This rate is not even close to doubling. It's only going up by a factor of 20%, 1.25. And so that means that we expect a barrier quite a bit less than 50 kilojoules per mole. It's a good idea always, to, if you can, to get some feeling for what kind of answer you expect, right? It helps prevent mistakes, helps you feel confident at the end that you got the right answer. The rest of it is standard Arrhenius. I guess I don't think we need to go through that in great detail either. It's EA is minus R log K2 over K1 divided by 1 over T2 minus 1 over T1. T2 is 310, T1 is 300, K2 is 250, K1 is 200, R is 8.314, and that gives a barrier of 17.25, indeed well below, much smaller than the 55K that we would have gotten if the rule of thumb applied, and that's consistent with what we expected to begin with. The second thing is for a mismatch, and it gets rates K2 at 300K and K2 at 310K, so the same thing except 60 here for the mismatch case and 70 here, and otherwise it's the same calculation, so just plugging in different numbers, 70 and 60 and 310 and 300 gives a barrier of only 11.92. Notice that barrier is actually smaller. It's inconsistent with what the problem says up above. I thought about changing this problem, but then I said, well, you'll get the right answer anyway if you do the calculations right. So that's probably not physically reasonable. The barrier really should be higher, though not much higher for the mismatch than it is for the good nucleotide. Anyway, it gives a barrier when you do the calculation of only about 12. And then it asks, by what amount does the mismatch raise the activation barrier? Well, it's the difference, right? 11.92 minus 17.54, which is minus 5.6. So it raises it by minus 5.6, which means it really lowers it by 5.6. All right, those are the correct answers, even though the problem is worded in a little bit of a funny way, and the numbers that I put in here aren't very realistic. And that is it for this session. We'll do another session